Audio Jungle. Audio Jungle.
Boundary layer flow, correct? See, remember this boundary layer flow is first of all highly viscous flow. It's a highly viscous.
सर स्क्रीन शेयर नहीं है क्या?
Is not shared. Highly viscous. It's a highly viscous flow. Highly viscous, and in this region, in boundary, where the boundary is forming, that boundary is what forming, their velocity gradient will exist. These are the single. I'm just writing. You make a note. First of all, boundary layer flow. It's a highly viscous, thin region. Very thin, very thin region. Number one. Number two. When a fluid fluid flow over a surface of over a surface of over a surface of any object, the object. The fluid velocity at solid surface at solid surface is zero. Will be zero, known as no slip condition. No slip condition. So it's very clear. Suppose this is what object, right? And this object is what is stationary, and fluid is what flowing over the surface of the this object. So over the surface or on the surface of the object, because this object is what object at rest. So whatever the particle due to adhesive nature, this particle velocity, okay, because it will be stick on the surface. So because of that, whatever the object velocity, the same velocity you will have for the fluid particle as well. Fluid particle. This is the condition actually. Okay, fluid particle velocity. Also, you see the relative velocity will be, but once you are going upward direction from the object, so this is the object is what as it is, this is what object is what is stationary, okay, stationary plate is what is stationary, plate velocity is what is zero only. now now we have a fluid flow. As I told you, exactly on the surface of the object the velocity will be zero. That, so that is nothing but no slip condition also called no slip condition. Object is what moving. Fluid particle will also moving with the same speed. So again, relative velocity will. Okay. But as you are moving in forward direction, as you are moving in forward direction, as you are moving forward direction, here, this is I'm talking inside the boundary layer. Okay, it is very short explanation I'm giving. The somewhat like this. See, somewhat like this. If you see the velocity here, it is zero. You are moving, start moving in forward directions. Velocity will be increasing. Okay, velocity will be increasing. Here the velocity is zero, but here it start moving like. Okay, here velocity is like this. So the velocity started increasing once you are moving in forward direction. Started moving forward direction. So here, if you check exactly the formation, this is called the velocity distribution over the surface of plate. See, this is nothing but plate here. Check, this is nothing but a plate here. And if you see the formation of the boundary layer, so formation. So here the velocity is what, zero on the surface. Everywhere the velocity is what, zero. Here the velocity is what, zero, but it start increasing. If you draw one vertical line, so you get the variation not like this. So exactly the velocity variation you will have something like this, and it is keep changing. See, if you draw here, pattern will be. So the point is, as well as you are moving in forward direction in the plate itself and in upward direction, you see the variation. See the variation here in especially in vertical direction. If you check inside the boundary layer, there is the change of velocity existing. Why it is happening? Because of the viscous effect, because one layer will oppose another layer. I hope you understood this. Because of the shear stress, I told you it's a viscous fluid. If it is a viscous fluid, if it is a viscous fluid, so as per Newton's law of viscosity, Newton's law of viscosity, that Newton's law of viscosity, that tau shear stress, tau shear stress, mu du by dy, mu du by dy. So when the fluid is what, viscous, this mu is what, it's a dynamic viscosity. Dynamic. What is this du by dy? This du by dy is nothing but velocity gradient. Velocity gradient in which direction? In upward direction. So du by dy, this axis you can say y. So everywhere, see, if you check the velocity, velocity is what changing along y. Along y, that velocity is what changing the y axis. And see the velocity component is along this, it is nothing but u. So basically, if you see, u is the function of y. Exactly, y is 0 means at the surface of the plate, u will be 0. Once you are moving in forward direction, see that velocity is what increasing. Okay, why it is happening? Because of the viscous effect, because of the opposition of the one layer to another layer. Because you see the Newton law of viscosity, it is tau. Tau is nothing but shear stress. If it is the highly viscous fluid, so there will be a shear stress, and obviously there is the shear stress, there will be a shear force. Shear force as well. Stress into area will give the shear force. The area is nothing but because it's a tangential stress. The tangential stress for the surface area will be the tangential, or surface area you can say. So tangential force will be acting. So this tangential force is just like a thin sheet for the fluid. If you check the layers, it's just like a thin sheet. So one sheet will be opposing another. Thin sheet means just like this. See, like this. See, this is what thin sheet. This is the one layer of the fluid. Please check it. This is the one layer of the fluid. And if you see the another layer will also be there, somewhat like I have to here the another layer of the fluid. Check it. The another layer of the fluid. So what is happening? If you see the bottom side, I told you the fluid particles here on the top of the not top, yeah, you can say on the top of the plate, or you can say exactly on the plate, the fluid particles velocity here it is zero. So these fluid particles is in a static condition. Why? Because the plate is what in a static condition. That is the no slip condition. If plate is what at rest, then fluid particle will be velocity will also be zero. And you also can say that is the relative velocity, because if plate is what moving, then whatever the particles which is attached to the plate, that particle will also move with the same velocity as the speed of the plate. But again, if you check the relative velocity, again it will be zero. So that is called no slip condition. Okay, so no slip condition is not only at static condition, it is at moving condition also. Moving condition also, if you check the particle velocity, it will also moving with, like plate is what moving with 20 meters per second. Whatever the particles are at the surface of the plate, that particles are also moving with the same 20 meters per second. So if you see the relative velocity, again it becomes zero. That is called no slip. So exactly on the plate, the velocity is what zero. So that if it is zero, so whatever the o, and if you see once it is increasing, that in upward direction, once it is increasing, so the bottom side layer of the fluids, it will try to oppose the motion of the forward. See, if this motion is what somewhat like this, so opposition means like this. So this particle, because viscosity is just like a friction, I can say. Okay, word I can say viscosity just like, so friction will, what it will do? Friction is basically acting between solid to solid, between solid to solid. You see the table. On the table, you keep your book and just push, apply tangential force. So you have to apply force on book tangentially. Then it will move on the surface of the table. But you have to apply continuous force. If you stop applying force, then automatically book will be stopped. Why? Because there is the resistance force, because there is the friction force. But if you same thing, you put the apply force, and it is on table, it is on glass. Okay, so if you apply less force also, that book can move from tangentially, it can move from one position to another position. Why? Because the friction force is less. So friction is basically opposing the motion. That is the idea I wanted to do. So, but it in case of the solid, that is the friction. Similarly, viscosity, that also the friction, but it is between the fluid to fluid, okay, or fluid to solid also, just like the below layer which is attached to the solid surface of the plate. So between fluid to solid also viscous effect can work, and fluid to fluid obviously. So it will oppose one layer to another layer. I hope it is very clear to all. So now because of this property only, any viscous fluid, if you because of this property only, any viscous fluid, okay, any viscous fluid will have a formation of the boundary layer. And boundary layer basically it is the very thin region. It is a very thin region, very thin region. I have to write this third point for this. Fluid velocity increases. Fluid velocity increases. I told you started from zero, and then it will be increasing with distance, from solid surface, from solid surface, and approaches approaches the magnitude of free stream. Approaches magnitude free stream. Meaning is very clear. See here, if you check this diagram itself, here the free stream velocity is, this is the free stream velocity. Free stream velocity means it's a completely undisturbed air. There is no disturbance at all. It is the undisturbed velocity. So until unless the object is not placed, the velocity there will be a free stream velocity, means undisturbed air. But once object means plate you have placed in between the fluid, so definitely whatever the flow passes over the surface of plate, it will not be free stream velocity. Why? Because of the viscous effect. There is the hinder, there is the disturbance, okay, and that is nothing but because of the viscosity only, okay. So now the flow will not be a uniform flow, will not be a straight flow will not be a stream flow now, because of the this viscosity effect, that near to surface of the plate there will be a disturbance, and it is very thin region actually. But it will try to oppose. See, exactly at the surface of the plate the velocity is what, zero. If you see, the velocity is nothing but zero, okay. But once you are moving, it is increasing. Means here if I say that this velocity is nothing but capital U, so approximate, this is the reason where the this is the outer edge of the boundary layer, okay. This is the outer edge of the boundary layer, so you can assume the velocity once it is approximate to 99% of the free stream velocity. If it is 0.99 of free stream velocity, means capital U infinity, I can. This U infinity is nothing but free stream velocity. So you can say inside the boundary layer, velocity started from zero and it start increasing in vertical direction, and it reaches to 99% of U infinity. Example, suppose U infinity, which is the free stream velocity, this is nothing but free stream velocity. Just say this velocity, free stream velocity of fluid. So you can say velocity of fluid. You can say here the free stream velocity is what, 100 meter per second. But if you see the variation in boundary layer, so it started from zero. It will start from zero, then it becomes 10, 20, 30, 40, 60, 80, 99 meter per second. Once you say it is reaches to 99 meter per second, and then you will say now the boundary layer is what, this is the outer edge, or this is the uh, that height of the boundary layer. After that you will get the free stream velocity. So this side again the free stream velocity you will get, means there is, you may say that now the viscous effect is what, not working here, okay. Viscous effect is not working here. So now you can assume again it's an out of free stream velocity outside the boundary layer. So inside the boundary layer you got the viscous effect. If this viscous effect comes, then it will be a rotational flow. But once you go outside the boundary layer, viscous effect will be negligible. And if it is negligible, then it will be treated as an ideal flow. It will be treated as a irrotational flow. These are the very important thing, okay. So always remember, inside the boundary layer it is very highly viscous flow. Many times I have told you, you please make a note of it, okay. So this is the very highly viscous flow, and if it is the highly viscous flow, so definitely rotational flow. Because if highly viscous flow will be there, then shear stress will be there, and if shear stress will be there, then flow will be rotational flow will be rotational flow. But once it reaches to 99% of free stream velocity, means now the viscous effect is what, negligible, it almost zero. So it becomes now ideal. Outside this boundary layer it becomes a ideal, or it is now the irrotational flow. Now irrotational flow. Please make a note of it. Outside the boundary layer, it is irrotational. Inside boundary layer, it is rotational. Inside boundary layer, it is called a viscous flow. Whatever the flow you will have, it is called a viscous flow, because viscosity is what dominating, and because of the viscosity, there is the resistance opposition between one layer to another layer, causes change of the velocity you will be getting continuously from surface of the plate to the outer edge of the boundary layer. But once you reaches to outer edge of the boundary layer, now the boundary is completed. I mean, outside this line, if you see this outside this line O to A, this side you do not have the effect of the viscosity. Means if you say the reason where the boundary layer is what available, it is now between O2, I mean below OA. Above OA, that viscous effect will not work. So you can say now the boundary layer is what completed. Now we do not have any uh, viscous effect. So that's the reason this outside flow called as the inviscid flow. But it is called inviscid. These are the few very, very important points. You make a note of it for single marks question. Every time you just be careful, okay? Sometimes questions ask you. So Always remember, if somebody asks to you define boundary layer, so what you will say? So you have to say the variation in velocity, okay, the variation in velocity uh, from 0 to free stream. The variation of velocity from 0, see here the velocity is what 0, and here it is outer edge is nothing but free stream velocity. So variation of velocity from 0 to free stream in the very thin region, the very thin region near to solid surface known as boundary layer, known as boundary layer. So if somebody asks to you what is the boundary layer, just define, okay, boundary layer. You can say this definition is now, you can say the variation, okay, the variation of variation in velocity or variation of fluid velocity of velocity velocity variation of from history from 0 to from 0 to history. History means 99%, 99%, not exactly the same. From 0 to free stream, okay. A very thin region, a very thin region, a very thin region, a very thin region near the solid surface, near the solid surface known as boundary. Hope it is very clear now. Basically, I have stated now how the boundary layer will be formed and what will be happening in boundary layer and all that I have to. Now, coming to the, I will show one single diagram where I will show the formation of the boundary layer happening exactly when the flow is what passing over the surface of the plate. Okay, so now take, now this is the plate here. See, this is the one example I am taking here. Take the, this is the plate. Okay. Now for this plate is what is stationary. This plate, it is called leading edge. This is called trailing edge. This concentrate. Now, and obviously this plate is what is stationary. So I have to fix this. This plate is what moving with zero velocity at rest condition. Now the flow is what now passing over the surface. So just before passing over the surface of the plate, the flow was something like this. This was the flow pattern actually. This is the called free stream velocity. See, this is the completely undisturbed air. The free stream velocity, which is called undisturbed air. Okay, this is called free stream velocity U, capital U, right? Capital U, capital infinity. This is called free stream, right? But once it started passing over the surface of the plate, okay, started passing over the surface of plate, so that formation, then again somewhat like this. Let's check. I'll show the different reason here, so more clear to you. What is happening basically? This is the till this is the one reason, this is the another, and then again another reason. Okay? So if you see, I have to increase the size length of the plate again, but anyway, you can understand here only. This reason, okay, this reason first, I can say it is started from A to B. I have to write A, B, C, and here I can take D. So between A to B, here the flow, whatever the flow you have, following path like this. But anyway, that velocity started that variation is here. I mean, existing here. The flow started varying in this region, no doubt about it. But it will be very smooth. It will be, you can say, well defined path. It will be in well defined path. it will be in well-defined path. Then once it passes, I mean, it reaches to B, C, so that flow will start here. I mean, combined effect will be there. It start moving in zigzag motion also, and then later on, it will have a. I mean, that flow will be zigzag, very high energetic. It will be zigzag, not in very well-defined path. So this reason, okay, this reason where the flow is what well-defined, it is called a laminar boundary. Yeah, okay. This is basically, I have to say this reason. This is called transition. Transition means that laminar flow will be converting into turbulent, and where the flow is what not smooth, not well defined, that region is called turbulent region, and that boundary layer will be called turbulent boundary. So this will happening. This is very the loss in turbulent boundary layer will be more and more compared to the laminar, because even though in laminar boundary layer also losses will be there. Why? Because it's a viscous region. But in case of the turbulent, as I have told you, momentum loss will be more and more because flow will not be well defined. There is the chaos actually, the turbulent region. So highly viscous, high speed flow. And so anyway, I hope it is very clear to all of you. Now, if you talk about the what is the boundary layer thickness, so that boundary layer thickness here only I will define. See, if you take this and if you draw the velocity pattern, I mean flow pattern. So this, see, this is called delta now. What it is called? Delta. Please remember this. The delta, you please. So this is called delta. So delta is the basically boundary layer BLT, boundary layer thickness. Boundary layer thickness means it started in boundary layer thickness. It started velocity started from u to u is equal to 0 to 99% of free stream. So the thickness here the velocity varying from 0 to 99% of free stream velocity, because this is the reason outermost reason here you will get the 0.99% of u infinity. Uh, Approximate the free stream velocity. So that thickness called the boundary layer thickness. You need to remember because it is very important actually. Okay? So if now now onward this two type of boundary layer you have, laminar and turbulent, and the reason, okay, if because this is the transition uh, zone, I have to say this is the transition region, better transition region. Here the laminar and turbulent both will be exist. Laminar and turbulent both will be existing. So much wake formation. This is called wake. What it is called? Wake. And whenever the wake formation will be there will be a losses. So after, see, the wake formation will be there. Wake formation means there will be a losses, separation of the flow from the surface. So many what happening. Okay? So I have to say the delta is defined as the uh, it is the thickness, perpendicular thickness from the surface of the plate, where the velocity is what varying from 0 to 99% of free stream velocity. You please remember, sometimes they can ask the definition in theory part. Okay, you need to remember this. And also one more thing I have to tell you, because as I have explained you that very close to the surface of the plate, the velocity is what 0. That is called no slip condition. So here this region itself, this region very close to the plate, this region will also represents like a laminar boundary layer. Why? Because here the velocity is very less. Why less? Because on the surface of the plate velocity is 0, so it will start varying, means 0 to 1 meter per second, 2 meter per second, 3 meters. So here again the velocity is very less. But if you see here, that velocity is and it is not well defined. So this question can be asked to you, where laminar sublayer can exist. So laminar sublayer will exist always in turbulent boundary layer. Okay, so this region is called laminar sublayer. Laminar sublayer. So the property of the laminar sublayer is always the same property what you have in laminar boundary layer. So this and this almost same. Why? Because the same nature it will show. Okay, because very close to the plate, the velocity is what very less causes it will be treated as a laminar boundary layer. So again, we cannot write the same laminar boundary layer. So we are writing sublayer, but the nature of this laminar sublayer will be exactly same as laminar boundary. I hope it is very clear, right? Now moving ahead, because we have to complete this session as well itself. So I'm skipping anyway. Check. So the basically the same thing. I mean, if you talk about the plate, please concentrate. You see this plate as it is. What we have here. This is the plate which is at static condition. The velocity here it is 0. If you have placed this, so doesn't matter that boundary layer will form only top of this. No, both side the same boundary layer will form. Same boundary layer will be formed, but generally we will be talking on the top of the plate just for explanation point of view. Otherwise, the formation will be same both side. Okay. So now if you see uh, uh, in transition point, this will be the transition point. Okay. You see, this is called a transition point. So I just want plot diagram. Ah, so transition point. See, so like this. So on top only I'm just doing. So this is the transition point here. In very clear, this is nothing but transition point. TP. What it is called TP. So this will be the laminar. Okay, this will be the laminar boundary layer. I have explained you what is the laminar and what is the turbulent, and this is the turbulent boundary layer. Turbulent boundary layer. Always remember it's very special. Okay, it's very special because question will be asking to you. So for plate that transition point, if you want to calculate the transition point, so how you will calculate? This length is nothing but L. So you know the formula R. So that R is now the critical Reynolds number. Critical Reynolds. What is the mean of critical Reynolds number? So it is a Reynolds number. Critical Reynolds. Please remember this. It's very special. So this is the critical Reynolds number where the laminar boundary layer uh, or laminar flow will be start will be starting converting into a turbulent boundary layer or turbulent flow. So in perspective of the boundary layer where the laminar boundary layer in end up and where the turbulent boundary layer is started. Okay, so that point is nothing but the uh, a transition point. Actually, it was a transition zone. If you see the transition region, but I have made it a single point now because the reason means existing both laminar and boundary layer or laminar and boundary flow both. Okay, but here if you see in terms of the flow, when the laminar flow and turbulent flow, the point where turbulent flow start flowing, okay, or where the turbulent flow start existing, that point is nothing but transition point. Transition point from laminar to turbulent. Transition point from laminar to turbulent. Okay, so this will happen at the critical Reynolds number, and this value for plate. Remember, it is very important. Okay, it is nothing but 5 into 10 to the power 5. This is for plate. Based on this question will be solved. Okay, very important. So for plate, this is the number, the critical Reynolds. So how you will find that is very important. So see how you will find it. Critical number. What is the formula? Rho V L divided by mu. This is the formula. So this L is nothing but the transition. Okay. If somebody asks you calculate the transition point, means the length where the turbulent turbulent boundary layer start forming. So that is nothing but LTP. LTP is the length of the this transition point. Okay, I hope it is very clear. So that time Reynolds number you have to take the critical Reynolds number from this point turbulent boundary layer start forming. Okay, and rest all the property like rho v mu will be given to you. I hope it is clear. We'll solve the problem so you will understand. Okay, so right. Anyway, now that also very important. You should know the velocity profile. Okay, with respect to the variation with respect to y. Y is the perpendicular distance from the plate. Na? This is the y coordinate system x. So along x, what is the velocity? Is u. Along x, the velocity is but u. Correct. And along the y, you are going to check how that boundary layer going to. Uh, uh, I mean, what will be the uh, pattern of the boundary layer, which is nothing but laminar boundary layer and turbulent boundary layer. So laminar boundary layer, you can see it will be forming like this. Check it. In very short, I'm just showing you. So you will get the idea. Huh? This is nothing but like this. So this will be the turbulent. Okay? Sorry, this will be the laminar, and the what is the check the pattern? It is nothing but parabolic. So parabolic shape. This is the parabolic, and if you see it here, this tip, this is nothing turbulent. So this is the turbulent. Uh, this one. Okay. So this is the basically logarithmic velocity profile I am showing you. Question can be asked you, what is the velocity profile in laminar boundary layers? You have to say parabolic. What is the velocity profile in turbulent boundary layers? You have to say right. Anyway, now very important. I have to discuss here, but the boundary layer thickness already I have. Now we'll talk about the displacement thickness. Okay. Boundary layer thickness and displacement thickness and uh, quantum thickness and energy thickness. These are the few things I have to start solving. As I have told you, check. First, we have a boundary layer thickness. Layer is it delta. कुछ देखो. Second is nothing but displacement. Second is nothing but displacement thickness. Displacement is denoted by displacement thickness. Is denoted by delta one. Denoted by delta one. Delta one or a star also you can take, guys. Then the third one is nothing but okay. So that moment got theta. Okay. Last one is these four you need to remember the delta I. Then we'll solve the problem. How to define this? Okay, all four. How to define this? Check. It's very easy for you. And boundary layer thickness already I have explained you. Layer thickness. Boundary layer thickness. Okay. This one I have already explained you. This is the plate here. And if you see the pattern of the formation of the boundary layer, so here the velocity is not this velocity is but u. Okay, u infinity. And the boundary layer thickness is nothing but the delta, the vertical height from the plate delta. Okay, the delta is the basically height, you can say. at in this direction we have a y variation. So at y is equal to delta, u is equal to 99% of, so where it you will get this 99% of the free stream flow, that vertical height is considered as a boundary layer thickness. So delta is nothing but it's a vertical thickness where velocity of the fluid uh, achieved 99% of the free stream velocity, called a boundary layer thickness. A boundary layer perpendicular distance surface where the fluid velocity is 99 free stream. That is called a boundary layer thickness, displacement thickness. Now see, you can consider here once the boundary layer is what formed here, which is basically dead region, you can say, where the velocity is what variation is very less and velocity is also very less because it is very, because it's a very thin region, it is close to the surface of the plate, na? So it is the flow, the total flow is what shifted actually. Why it is shifted? Now I will show. Suppose see, this is the circular pipe. Check, this is the circular pipe like this. This is the circular pipe. So if I ask to you, just show the boundary layer formation for this. So how you will show? You will show somewhat like this. You will show this is the boundary. So if you, I will ask what is the annular area or what is the area for the fluid flows. I have to say the area actually. This is the basically area where the flow is what flowing. Rest this side is nothing but the dead region. What is the reason? Dead region. Why it is dead region? Because velocity is what of very less, approaches to zero. So because of the formation of boundary, as I have told you in and other time also I might be discussed, because of the formation of the boundary layer there will be losses actually. Okay. I had shown that work done factor in axial flow. So I had shown you that for because of the for how that parameter was changing, compensate that we had multiplied by the omega, that was the constant 0.98 work done factor. If you, anyway, so the point is, if the formation of the boundary layer will have, if the formation of boundary layer will have, then what is happening? There will be a loss. That is nothing but mass flow rate. It will be shifted. So I have to define now. In the same idea, I will define the displacement thickness. This will also be asked in exam. Displacement. So basically, this displacement thickness comes into picture because of that deficit of mass only. So what you will write? The mass flow rate. The mass flow rate. So the mass flow rate within boundary layer. Please remember this, within boundary layer is less than less than the flow rate, less than the mass flow rate in absence of boundary layer. I hope you understand because I have shown the diagram here also. See, if there is no formation of boundary layer, so the full diameter you will have for the flow, for the fluid flow, full diameter. But now this is the diameter. See, this is the diameter where the fluid is what flowing. So obviously mass flow rate will be less only because what is the mass flow rate? M is equal to rho area into velocity. So this area is what reducing once the formation of boundary layer you will always remember. Always remember. So now, so if you define well for the what is the displacement thickness mathematically, so the displacement thickness is nothing but, I would write here, it's nothing but delta star. Mathematically delta star is nothing but 0 to lambda, because till where the boundary layer thickness we have till delta, so 0 to delta, it is nothing but 1 minus u. U is the velocity, small u. with the velocity inside the boundary layer divided by u infinity, which is the free stream. You have to integrate from 0 to delta, you will able to find the displacement. This is the formula, okay? Formula. I have given the diagram multiple time, but more time I am just giving. See, check. So this is the basically delta here, okay? This is not delta. So the delta, because here its outer edge the velocity is, but say it is 0.99 of infinity, and this side velocity is what you have written here, and this side velocity is nothing but u, is varying. Okay. So in this way you can calculate the displacement thing. This way you can calculate the displacement. So basically you are going to calculate the displacement thing. So you are uh, going to the check, or you going to the calculate the deficit of mass just before boundary and after formation of boundary. Always remember. So that calculation will be done by the displacement thickness. Calculate the mass flow rate of the mass flow rate of uh, basically flow before formation of boundary and after. Whatever the deficit you are getting, that will be compensated by the displacement. Boundary layer will be shifted in upward direction with the displacement thickness to compensate the loss of mass flow. Okay. Boundary layer will be shifted. So that distance with what it is shifted called the displacement thickness. I think it is clear. That is the physical significance. Now coming to the momentum thickness, because once mass flow will be uh, mass in mass flow, if there will be a deficit. Why? Because the formation of boundary layer. So to compensate the deficit of the momentum, okay, because if mass flow is what changing because of the formation of boundary layer, so momentum will also change. So to compensate the deficit of momentum, the boundary layer will be shifted in upward direction. That distance with what it is shifted called the momentum. So I can write this. This is the very I mean generic definition. I can write this also. To compensate, I will write this also. Okay. To compensate the mass, compensate the momentum deficit. Okay. Due to formation of boundary layer. Boundary layer. Boundary layer will be shifted in direction perpendicular to the plate. In direction perpendicular to plate, called, this is the physical significance, called momentum thickness. Called momentum. How you will calculate this? Delta star. Sorry, thickness is nothing. Theta. So how we will calculate this theta? Theta is nothing. Still formula. This theta is nothing but momentum thickness. 0 to delta. Okay. U by U infinity. 1 minus I. They will be given. Capital U is the free stream velocity, which is constant. So small u value will be given, and that will be the function of y, because u is changing in from the direction of y. So it will be the function of y. You have to integrate it from 0 to delta, and if you integrate with respect to pi, with respect to pi, so you get. So similarly, you will get the energy thickness. So what energy thickness indicates? Energy thickness. So this will indicates momentum loss. This will indicate momentum loss. Okay, the previous one, displacement thickness, this will indicates mass flow rate loss. Mass flow rate loss. So to compensate the mass flow rate, boundary layer will be shifted. With what distance it is shifting? That is called displacement thickness. Displacement thickness means the boundary layer is what displaced, compensate the loss of mass flow rate. Okay? And that is naturally, by nature it is shifting. Similarly, momentum thickness indicates the loss of momentum or momentum loss. And to compensate that boundary layer will be shifted. Okay, that will be called as a momentum thickness. Now we'll talk the energy thickness. What energy thickness? It's energy thickness. It's nothing but delta A. So it indicates energy thickness indicates the loss. Compensate the energy loss. And why it is always there? That loss, momentum loss, mass flow rate loss, energy loss. Why? Because there is the formation of boundary layer. Okay? I hope it is very clear. So to compensate this energy loss, the boundary layer will be shifted by delta E distance, and that calculation you will by 0 to delta by U in bracket 1 minus by U infinity square. All right, this is the formula. In general, I just want to write in general. Always remember delta is boundary layer thickness is highest. Then you will have a delta star, which is what moment. Then you will have sorry. Then first is boundary layer thickness, then displacement thickness. Then you will have a energy thickness. Okay, then last you will have a moment. So in general, this is happening. Uh, I mean, after calculation and all. Okay. So anything you can calculate. I mean, it will be very easy for you. Anything you can calculate. Just like example, if you see one velocity profile, it is given. See, velocity profile is given to you like u by u infinity. See, this is the velocity profile. U by is the function of y. I told you 2y by delta minus by delta. Now, if it is asked to you, find what uh, is the basically a displacement thing. Is the displacement thing by star. Have to calculate is the momentum thing theta. How you will calculate? It's very easy for you now. If I ask you calculate delta star, so what will be the delta star? See that formula I have given. It. Delta star is nothing but 0 to delta 1 minus by u infinity. So 0 to delta 1 minus by okay into d. What you will do? Delta star just keep 0 to delta minus u by u infinity by delta plus minus minus by square. Just integrate with respect to delta star, which is nothing but displacement thickness. Easily you can calculate. What you will get? See here first you will get delta dy integration limit delta. This is 2y square by delta. 2y square by 2 delta 2 to cancel out. You will y square. Y square, so it's nothing minus of delta square by delta plus. It's a y square you have, so it becomes y cube divided by 3 into delta. So y cube, keep the limits to delta cube divided by because this is also delta square. So 3 by delta square. That's all. Solve with delta square by delta minus delta cancel out. Get the delta cube by 3 delta square. So one delta will be there. So this is your this will be such type question he asked you. Okay, so please remember this. Please remember, I told you was because of the very short time of I'm just trying to finish it in very short. So this type of question can be asked number. Second one more important is nothing but safe factor. They can ask directly what is the safe factor. Safe factor is nothing but h. It's nothing but the displacement thickness delta star to momentum thickness. Yeah. This parameter can ask you. They will give the velocity profile. They will ask what is the safe factor. So factor you just calculate the displacement thickness and calculate momentum thickness. For this problem, I have calculated delta. I hope you everybody understood how to calculate delta star. No? Delta star I have calculated. Similarly, you can calculate momentum thickness theta also. Similarly, you can calculate energy thickness. So it's a very easy task actually. Not difficult. Easy. Correct. Now, as I have given the transition of boundary layer, I am now to turn. So what is the formula I have given? C to check. That is nothing but first I have given for the transition, which is 5 into 10 for 5. Then always remember, if I will say the transition is, make a note of this also, transition. Okay, transition of boundary layer from laminar to turbulent. Okay, so you have the formula Rex, that is nothing but phi or pi. See, that means if you are going to calculate x distance in terms of x also they can be asked x. So what is the formula of the Rex? Rex, they are talking rho b OB or u, because it's a cost is OU x divided by u. This is the formula that will be equal to 5 into 10 or 5. Sometimes they will give the kinematic viscosity. So u is nothing by rho is nothing but nu. Kinematic viscosity. They can give the kinematic viscosity. U is the dynamic viscosity. U is the kinematic. This is the dynamic viscosity. You should know this. This is the dynamic viscosity. What is the? I hope it is very clear. Huh? Any confusion? Okay. Anyway, dynamic viscosity and kinematic viscosity. This unit kinematic viscosity is, I think, if you check the unit level 9. Viscosity and dynamic viscosity unit. In Newton second per meter square, uh, we have a Pascal second. That is the second per meter square is the right Newton second. I don't remember the dynamic viscosity and calculate this also. Kinematic viscosity also you can calculate. Right. So you need to otherwise you may wrong answer. Dynamic. Okay. Right. So now one thing I have to tell short, which is nothing but the calculation of the boundary layer thickness For different velocity profile, we have a different formula. One general formula I'm just that is called uh, that Blasius solution, which is very important. Okay, so you just write down Blasius solution. This is the final thing. So I just want to Blasius Blasius solution. So this Blasius solution basically it will work for the calculation of boundary layer thickness. It work for the calculation uh, skin friction drag, and it will be basically defined for sense of velocity profile. If there is no velocity profile, just like the first one, see, I had given this velocity profile. See, this was the velocity profile. This is called a velocity profile. Check. This is the velocity profile. So for the velocity profile, if they have given, then easily you can calculate for that. But if they have not given velocity profile, so absence of velocity profile, absence of velocity profile, and then you how to calculate the other parameter. Like number one, what you are going to calculate here, first unit, right? You are going to calculate with the Blasius solution. You are going to calculate the boundary layer thickness. How you will calculate thickness? How you will calculate boundary layer? Nothing but how you will calculate. So as per the Blasius solution, it is derived formula. You just remember the formula. Call it's nothing but delta is equal to pi x divided by root of r e pi x root of r e. This is the formula for the boundary layer thickness. Second formula is write down phi x divided by root of rex. What is the x? See, it's nothing but so anywhere at distance x. If you want to calculate, this is the at this distance. What is the delta? You want to calculate formula. What is the rex? False number at distance x. It's rho u x divided by simple formula. So this Reynolds number, as I have told you in terms of kinematic also, you can write u infinity x divided by what is mu by rho, also called nu, kinematic viscosity. This will be the formula, okay, phi x by. It is for the boundary layer thickness. The second parameter, what you can calculate, you can calculate second number, you can calculate the local skin friction coefficient. Friction coefficient. And what is the formula? It's a Cx. It is nothing but 0.4 divided by Re. Rex is that, as I told you, it's a Reynolds number at any distance. O E or U x divided by. So at x distance, you will able to find what is the local friction coefficient. This is the second formula. Third is very special, very important. These are the things they are asking. Till they have asked this. This is related to the laminar boundary layer. Remember, third, what you can find. The third one is not called average drag coefficient or means over the surface of plate. What is the average drag coefficient? This was the local drag coefficient or called skin friction coefficient, means at any distance x. But if you calculate the local, if you calculate the average, so it will be for the complete length of the plate. So that will be nothing but I have to write CD. CD. CD is nothing but 1.3 of RE. Please remember this formula. Help you. REL is complete length of the plate. REL by. See, what is the mean of this? Meaning is here now the full length of the plate you will be taking. Length here, taking a any distance here you are calculating friction. Correct. I hope it is very. These three formula I have given. I'm sure with the help of this you will. So this is the one thing. Second thing, check by boundary layer thickness. I will give a few points which is important for this. Write down the important notes. What is the important notes about about boundary layer? About boundary layer. See, if you check boundary layer thickness, huh? About boundary layer thickness, I must. This also they had asked you for laminar. How the laminar boundary layer delta is what changing. See the formula at seen. What is the delta you have seen? It's as per Blasius law, phi x by root of Rex. We have a phi x in root Rex is nothing but rho ux by mu. So 1x is what in root. In numerator you have x, in denominator you have root x. If you see x you will get. So delta is always directly. This was very important. It is asked in your exam. This is for the laminar boundary. This is asked in your exam. And I will write a turbulent boundary layer. Oh, turbulent boundary. So how the delta is what changing for the turbulent, that also very important. Delta is nothing x to power 4 by 5. That x to power 4 is remember. Okay. 4 by 5. The value for the turbulent boundary layer. As I have that was boundary layer, if you check for the smooth plate, delta by x. This is the formula for turbulent. It's nothing but point x divided by Rex. Not in root. Not in root. I have to write power. This is the formula for the turbulent. It this much I have given for the boundary layer. As I have told, like this subject, so much things are available to 3D point of view. Like you can understand if you talk about the delta. Talk about the delta. How delta is what related with the turbulent. How delta is related with the infinity for the laminar turbulent. So I can say note first you had written the important note for first. This is the second and third you need to write third. You need to write this that delta boundary layer thickness decreases as 2 infinity increases means free stream velocity increases, so delta decreases. So delta is always uh, um, reciprocal of infinity. Take the formula, get it. Fourth point. Fourth point. Delta always increases as kinematic viscosity. Kinematic viscosity. This is the kinematic viscosity increases. So actually, delta is directly. Take the formula, you will get it. Okay, whatever the formula I have written, from there only I am writing. Right. And fifth, that stress. Okay, that is stress. Shear stress tau. Shear stress tau for laminar. Laminar is directly proportional 1 by root x. 6 number shear stress tau for the turbulent. It's directly proportional to 1 x power 1 by b. You please see the formula, you will get understand this how it comes. But this is the important note conclusion I'm writing, but it is already for I have written the formula to understand. Right. All right. So see whatever the information I have given to you, problem is I have tried to solve this. The laminar boundary layer. The laminar boundary over a flat plate. Flat plate held parallel to the free stream. Free stream is 5 mm thick at a point meter and downstream of leading edge. Thickness of boundary layer. Thickness of boundary layer at a point 0 point downstream downstream of the leading edge. The leading edge will be option 20 mm, option C 5 mm. Take it. This problem they have asked for the laminar boundary layer. They are simply asking the delta value. See this, they have said this is the one plate. Okay, clearly they have mentioned plate, right? Like this is the plate here, and for this plate, there is the formation of laminar boundary layer. Clearly in the problem they have mentioned. They are taking two different point. Okay, they are taking two different points. This is the velocity profile boundary layer, laminar boundary layer. See, first case what they have given, the laminar boundary layer over a flat plate held parallel to the free stream 5 mm thick at zero point 0.2 meter. Okay, and then next point is 0.8 meter. So this is just say 0.2 meter and 2 meter, and then this is next one is nothing but 0.8 meter, right? It's a meter only, right? 0.8 meter. And for the 0.2 meter, the boundary layer thickness they have given. See, the parallel free stream is 0.5 mm thick at point 2 downstream. So 0.8, they are asking what is the thickness of boundary layer. So here they have given this thickness, they have given nothing but they have given 5 mm. Okay, so just say this is the point 1 and
सर आंसर क्या है?
I don't know, you have to check it. So what is the condition for boundary layer I have given? If you
सर
see
220 आ रहा है।
the formula, delta is nothing but directly proportional to root x for the laminar boundary. Correct? So see delta root of x for the laminar boundary layer LBL. So delta 2 divide, because they are asking delta 2 at this point, they are asking this, right? So delta 2 by delta 1, what you will get? Of x2 by x1. If you see it, delta 2 is nothing but delta 1, which is 5 mm thick. X2 is nothing, 0.8 divided by point. How much it is? 10 mm. If that option is there, see this option is there or not?
Yes, sir.
Ah, I hope it is clear to all of you. This was the gate problem. Well, you have shared one problem. I will solve that also. This one is clear, correct? Yes or no? Is this clear? For the laminar, you have
Yes,
to
sir.
use this relation, right? Now we'll be writing the your problem you have shared, right? So this is also gate problem. This was asked for 2 marks, I think. 1 marks.
2 marks, sir.
Right. The question is the thickness of laminar boundary layer laminar boundary layer of laminar delta over a flat plate. Formula is also given over a flat plate is, they have given the formula delta by x is 5.2 of REF. Generally, Blasius solution is phi. Okay, phi of root of 5 divided by root of Rex. But this is not a Blasius. They have given by for any velocity profile, they have given this boundary layer thickness. Nothing to worry. By 5 point they have given. They can give. They are giving means they somewhere they are using different velocity profile. So where x is measured, x is measured from the leading edge along the length of the plate. The velocity profile within boundary layer, the velocity profile within boundary layer is idealized as varying linearly with y for free stream velocity of meter per second and kinematic viscosity, okay, of 0.5 10 to power for minus y, right, by meter square per second. The displacement thickness displacement is of at displacement thickness at 0.5 meter from S is in mm. Anyway, so here first of all you select this delta by x, okay? Because if you are going to calculate the displacement thickness, because in the problem what they have asked, Simply they said displacement thickness. You know displacement thickness. I have given the formula delta star, which was 0 to delta 1 minus u divided by u infinity. This was the formula, correct? Yes, so this was the formula. So, and you have to integrate from 0 to delta. So for that, this delta should be known. So what is the delta formula they have given in the your problem? See what they said. They said 5.2 root of Rex, correct? So 5.2 x of root of Rex. So first of all, we'll calculate delta. So what is the delta formula? See, delta, they have given 5.2 x root of Rex. Okay, what is the Rex? It's nothing but rho Vx by mu. And you know, Vx divided by mu by rho is nothing but kinematic viscosity. So Vx divided by nu. Check all the parameter given or not. See what is the velocity they have given. Velocity they have given 3 meter per second. And see distance they have given to you or not. Somewhere kinematic viscosity is given. Okay, true. See any distance they have given. See the problem. Written not x should be known. Otherwise, how you will calculate? X should be known. See any x distance is given to you.
Yes, sir. 0.5 meter.
And the displacement thickness. Just a second. 0. Displacement thickness they are asking 0.5 meter means they have given x directly. So velocity. Tell me dear again what is the velocity they have given? Go back and check. 3 into x. Basically, I will draw the diagram for this so it will be more clear. Here they are asking the value. Here they are asking. See, this is basically delta, but here they are asking delta star, which is placed at 0.5 meter. I think now it is clear. 0.5 meter or meter, no? Yes.
Meter,
So,
sir.
right. So now here first you calculate delta. Sorry, this is Rex. No? So first you calculate delta here, then only you will be able to find delta star. So Rex you will have 3 into x 0.5. And what is the new? Please check it. What is the new? Yes. It's a 1.5 10 to power minus 5. 1.5 10 to, please calculate this, Rahul. How much you are getting relaunch number? Yes. 3 into 0.5. 1.5. 1.5 cancel out 10 to power 5. Check it. Yes or no? So, right. Agree with me? Are you getting this? Are you getting this? Rex is nothing but 10 to power 5. See, 3 into 0.5, 1.5. 1.5 numerator and
Sir.
so delta is nothing but 5.2 into x is nothing but 0.5 divided by root of 10 to power 5. Can you calculate this? Calculate this. Quick. Find it there. Calculator. And 5.2 into 0.5 divided by root of 10 to power 5. 10 to power 5. So take the root of 10 to power 5. Quick.
8.22 mm.
8.22 mm. You are talking mm, okay? Because this 0.5 was in meter. Correct? 0.5 was in meter, na?
Yes, sir.
Yes. So you are giving your answer in mm. That's okay. I don't mind, but you remember the unit as well. Huh? So this is at 0.2 mm. Now delta you have. What you have to do? See, to calculate the displacement thickness, you have to keep a delta 0 to delta limit and one u by u infinity. So this u by u infinity is the main things you have to calculate. U by u infinity. So what is the function? See what they have said in the problem. You read nicely what they have said. The velocity profile within boundary layer is idealized. They said it is idealized, but actually it is not the linear variation because the that is the one condition which is the Cauchy flow actually. In Cauchy flow you will get the linear variation. But anyway, so I will show you what is the mean of it they are saying. I am just trying to explain you. Check. They said this is the plate, okay? This is the plate here. Over this plate we have a formation of boundary layer. See, recently I have told you that if you want to draw the uh, anywhere, if you want to draw the velocity profile, the velocity profile I have shown you parabolic like this. But what they said, it is now idealized. It is now idealized. So what they have taken now, as per their uh, uh, given statement, they said it is idealized. So idealized linear means like this. Idealized like this. So what is the velocity profile? The velocity profile is now velocity profile. Check it. I hope it's clear to everybody. See, it's nothing but you can say. See, this is nothing but measuring. You are measuring from 0 to y. So if it is at y, so at y, velocity is nothing but u, and at y is equal to delta. What is the velocity? Is nothing but u infinity. 99% means u infinity. So overall, the thing you can, if you write the profile, so y by delta is nothing but u by infinity. That's the idea actually. So you can say u by u infinity here because it's a linear variation with respect to along the direction of the along the vertical direction. So it is y by delta. So this is the linear variation. This way you can say it's a linear variation y by delta. See, if delta becomes 0, so u will be 0. You can check if y is 0. Okay, if y is 0, u will be 0. If y is delta, u will be u infinity. Check. So by this way, here you can write u infinity, which is constant, y by delta. This is varying. Now check the boundary condition. If y is 0, u is 0. True. If y is exactly delta, then u will be u infinity. Means it is satisfied. So this is the linear variation. Okay. Now if it is a linear in this way, you have to check boundary condition and all. Okay. So you got u by u infinity. Now your problem is sorted. By u infinity is y by delta. Can you calculate delta star? It's a 0 to delta 1 minus u by infinity dy. Integrate it how 1 minus u by infinity is y by delta. Check dy. Started from 0 to delta. Do it how much you will get? It's a delta after integration y square by delta. Y square by 2 delta. Na? It's not y square. That put limit, so it's a delta square by check how much you will delta minus what delta by. So what is the delta star, which is displacement? What is the delta you have calculated, Madhuri? Quick.
8.22.
8.2 sorry 8.22 by 2. How much it is? 4.11 mm. You had calculated in mm, right? They are asking value in mm. Two decimal. Who has Rahul? I think you have asked question. Can you check your answer now?
Yes, sir.
Huh? This is the answer? Yes or no?
Yes, sir.
No, no. You cross checked? Is it
Yes, sir. 4 to 4.2 तक का.
correct? Correct. It is accepted.